Okay.
So if you're watching this video, I'm just now starting to record. We already have 2 pages of notes here. Looks like people often don't watch the recordings anyway, so I apologize for that. So we're starting in with the recording right here. Okay, what's your question, Ritvik?
So for sets, I noticed that I kind of got like most of the problems incorrect, though I'm gonna figure out like how to kind of understand like um like the set without having to draw a number line. I know the number line helps, but if you're in a test, it just might be a little time consuming and kind of tedious because I'm not sure if you're going to include fractions or decimals in the set.
Mm-hmm. Well, it really doesn't take that long to draw some sets. You don't
Okay.
have to make it super,
Like
crazy perfect.
precise?
Yeah.
Okay.
But,
Because,
if you at least kind of, like when we're looking at A1, that's -1 minus 1 over 1 to +1 plus 1 over 1. It's -2 to 2. But, you don't have, it's from -2 to, to 2. You can just put the solve brackets and just quickly do that. There you go. It's right there.
yeah, but so ace of one, so whatever ace of one would be like the end point for the sequence.
I don't know what you mean by the endpoint for the
Like
sequence.
this is ace of one, that's the initial term.
We're not viewing this necessarily as a sequence. I suppose you could view this as a sequence of sets where the first set is A1 and the second set is A2 and the third set is A3. I mean, we don't generally at this level think about sequences of sets, but the point is you do need to understand, what these sets look like, and so A2 goes, you know, so if this is -1 and this is +1, so from -3/2, which is here, to +3/2,
Okay.
and then, A3, it gets closer and closer. In fact, you almost kind of want to not even worry so, but you don't realize this until you've really taken a look at it, that what's really going on is happening, in here between -1 and -3/2 and between 1 and +3/2. All of the endpoints start appearing, in here. And they're nested sets. So you
Yeah,
can,
I know they're nested, but
yeah.
if we were to find like the union,
Well, they're all contained in that first set. So, in that sense, thinking about this as a sequence, if you understand that each A sub I is contained in A sub I minus 1, like A sub 2 is a subset of A sub 1 and A sub 3 is a subset of A sub 2. If you realize that, then suddenly it is pretty easy to see that the very first set, A sub 1, is the biggest. And since all the others are contained in A sub 1, it will be the union.
okay, I'll keep that in mind, but thank you.
This was an interesting little problem because I asked for the intersection so I can correct the notes here of the A sub k as k ranges from 1 to infinity. And if we just think about what happens, these sets, they do get smaller, but they don't get infinitely small.
Mm-hmm.
You know, the point is, if you graph it, and this is where a picture really does come in very handy, unless you have a pretty good intuition about fractions, which is also good to have a good intuition about the relative sizes of fractions. But this is minus 1.25. This is minus 1.33. This is minus 1.5. This is minus 2. But the point is, no matter how many of these you list, you're always going to have, some people wrote -1 minus 1 over infinity, +1 plus 1 over infinity. That's a great intermediate step. But the point is, this gets small, this term, 1 over infinity, approaches 0 as infinity, gets large.
I know. So, like, if the denominator is like, if it keeps growing, then it gets smaller.
Right. But the point is -1 and +1 are always going to be in all these sets, because all these sets, they sneak up on -1 and +1, but they never actually achieve -1 or +1. So the intersection actually is this interval. -1 and +1 are in all these sets. Because this,
Oh, okay.
and that was the mistake that I made on the office hours on the 20th of November. Is I was tired, and I thought, oh, -1 and +1 aren't actually also included, but it's all these elements between -1 and +1, including negative. It's an infinite number of numbers in there.
Oh, okay.
I am pleased that most people are seeming to understand that these sets are infinite sets. There's an infinite number of elements in there,
Mm-hmm.
lots of numbers in there, but we actually do include the -1 and the +1 in that intersection.
Okay.
Was this problem number 4 or 3A? I can't remember what number it was. Was it number 4A?
Let me pull up the special homework.
Oh, don't worry about it. Don't worry about it. I thought you had it in front of you. All right. Next question. Does somebody else have a question?
Yeah, can I get a little help on the special homework number 9? What was it? Question 5.
Yeah, yeah. Number 5 was one that was just like one we did in class. Let me just see if I can figure out which class we did this problem basically in class. Let's see, whenever we did so I guess it was day 19 class, when we were working on induction proofs. So on day 19, it's taking my computer a minute to load this up. Um, we proved 4 divides 5 to the n minus 1 for all n greater than or equal to 0. So we did prove that. Okay. And is anybody else drawing a blank with a few of those pages on that? It's weird. Anyway, but the point is, we're proving that 10, or was it 11 divides 10 to the n minus 1, right?
Yep.
For all n greater than or equal to 0. So what part of that did you have trouble with? The basis case or the induction step?
Basic basic step.
Okay. So in the basis step, what's n naught? What should we let n naught equal?
I believe NO be
It's 0. We're told
yeah,
where to
0.
start. Okay, so it's 0. So we wish to show that this statement is true when n is 0. So we wish to show p of 0 is true. Let's look at what we really want to show, i.e. we wish to show
Oh, sorry. It's actually 10, was it 10 into 11 n minus 1?
oh,
Yeah, sorry.
no, that's fine. Yeah, of course it is. 10 divides 11 to the n. Yeah, this has to be one smaller. Okay, so we wish to show that 10 divides 11 to the 0 minus 1. But it's good to unpack that wish. What does it mean to say 10 divides 11 to the 0 minus 1? It means 11 to the 0 minus 1 is a multiple of 10. 10 times m, where m is some integer. So that's our wish. And also unpacking the wish helps us realize we need to look at this. We need to look at 11 to the 0 minus 1. So we just look at that. What is 11 to the 0 minus 1? Well, what's 11 to the 0?
That would be 1.
Good. So we're looking at 1 minus 1. So what is 1 minus 1?
0.
Now we have to show that this is a multiple of 10. So we have to show that this is equal to 10 times an appropriate integer m. What m will work?
0.
Yeah. So you have to show that. Because if you just show this is equal to 0, that doesn't have anything to do with being a multiple of 10. You have to show that 0 can be expressed as a multiple of 10, namely, like you said, 10 times 0. And we just, mentioned, hey, 0, 0, I'm talking about this copy of 0, is an integer. So 10, divides 11 to the 0 minus 1. And p of 0 holds, or is true. That's it. Does that help?
Yeah, that does help. Thank you.
Uh-huh. Other questions? I was surprised how few people asked for scans of their graded homework number 10. But I sent it to everybody who asked for it. I'll also be in my office tomorrow afternoon from 4 to 4:50, 4:05, 4:10 to 4:50 if you want to come by and pick up your graded homework 10. Other questions? Hey, Sean. Hey, Trevor. Hey, Anticott. Who all's in the room? Sean. Yeah, hey.
Can you explain about the onto and one-to-one about function thing?
Explain about onto and one-to-one.
Yeah, we got, and also we can work on the.
Have you checked? All right, so do you know the definition of onto? Did you look it up in the notes?
Yeah, I did.
So we've said it so many different ways. A function f from a to b is onto if, do you know, did you review any of those?
Yeah, I was reading.
Okay, so you need to practice because you need to be able to write that. But here, if every element, little y, in the codomain B appears as a second coordinate in some ordered pair. And I think you could say, at least once in some ordered pair, x, y. In other words, for all y in B, there exists an x in A such that xy is an element of F.
Dr. Good,
Yeah.
if I say if there's a question about onto, can I use the arrow analogy? Is that okay? An arrow hits
Every
this one.
y in B gets hit by at least one arrow. Yeah, we've said all of these different ways.
Hmm.
That'll be fine. And that's one of the reasons why I've used arrow diagrams, is they seem to be helpful. So Anticott, does that make sense for onto? These are all, these are all different ways.
Yeah, yeah,
Okay.
that's
And so a function f from a to b is 1 to 1. You need to mute, okay? If each y in b appears, instead of at least once, at most once as a second coordinate in some ordered pair, x, y. Or you can think of it like this: if f of x1 equals f of x2, then that forces x1 to equal x2. Or if you want to think about arrows, every y in b gets hit not by at least one arrow, but gets hit by at most one arrow. You can't have something getting hit twice. And we had lots of examples, and you should look over our examples. We had lots of examples where we went over onto and 1 to 1, right? So especially in the function worksheet, and the solutions are posted, you should just look through those examples and read, what's written there for those. Was there a particular problem that you were having trouble with?
no. Oh,
So I'm not up to making up more problems right now, because I put so many different problems up already.
I know.
You should look over those
Okay, thank you.
from the notes and from the function worksheet. Welcome. Other questions? I'm going to pause the recording until somebody says something. Hang on.